Good. Okay, so welcome back. So this is the fourth lecture and the last lecture of p-adic functions on ZP. And let's first of all recall what we claimed last time and didn't get to give a complete proof, which is that we consider the space of continuous functions on ZP with coefficients in F in QP, where the norm of this p-adic, like the norm of the function, uh, is defined to be the maximum of for all the elements in ZP of the p-adic norm of the values of F. So that gives a Banach norm on this space here. And what we're trying to prove is that these polynomials, we have seen that these, when we plug in values x in ZP, that these will have values in ZP, taking binomial coefficients in some sense. And they will form an orthonormal basis of this space of continuous functions on ZP with values in QP. So in particular, what that entails is that every continuous functions on ZP with values in QP can be written uniquely in the form of sort of a kind of linear, it's an infinite linear combination of these Mahler bases with coefficients in an. I should write here an in QP, and the p-adic evaluation of an goes to 0. And the basis that we have over here, the binomial basis, is called Mahler basis, named after, I guess, the mathematician Mahler. And this expansion here is a Mahler expansion. So let's quickly recall what we did last time. We said, okay, we observed that we can simply, by evaluating my function f at these 0, 1, 2, this integer, natural numbers values, and then we can actually deduce what this a0 and a1, a2, the coefficients are. If I go on, I can get a list of all the numbers an. And in fact, we can do it more systematically, in the sense that I take the sort of consecutive difference of these functions f, in the sense of fx plus 1 minus fx, and then continue on, take higher and higher orders of differences. And this looks somewhat like the taking differentials. So there's just some theory about difference operators versus differential operators. So this is kind of like a difference operators. And I'm going to assume that if I assume that Mahler expansion holds, then if I take the first difference, what happens is that basically you shift this x choose n into x choose n minus 1. And then if I do it if I do it m times, I just basically shift this n minus m. And in fact, I get to greater than equal to m here. Basically, if I have sort of negative number here, that's considered 0. So therefore, if I evaluate this sort of mth difference function at x equals 0, I get the am being this mth difference function. And if you think about this, really looks like taking sort of a derivative of a function and evaluate at 0, then you get all the Taylor coefficients. So but we're taking the difference operators instead. So this argument we have over here last time explained says that if we had this expression or sort of linear combination of these binomial coefficients, if it exists, then it must be unique. So now I want to say that, okay, I start with an f. I can always form this. If I start with an f, I can always form these difference functions, and therefore I can evaluate at 0. So I get some am. And of course, I need to show several things. First of all, that these an, if I define this way, the p-adic norm will go to 0. And the next thing that's actually the infinite sum we have over here is actually equal to fx I started out with. So basically, I need to show, starting with f in continuous function ZP with values in QP, I can really define, if I want to, am being fm 0 for all m. And I want to show, which is somehow the second step, what we do here is that the p-adic norm of this, I define this. So the p-adic norm of this will actually go to 0. as m go to infinity. And maybe just list all the steps I want to show. And the third step will be I will actually show that fx is actually equal to the sum of am xm. And finally, with all these at hand, I will show that each one of them, if I take the Banach norm on this space of continuous functions on this one, excuse me, this is just one. And if I take the Banach norm of fx, that's really the maximum of all the p-adic norm on each of the coefficients in that modular expansion. And therefore, all these three steps will show that these will show our theorem, namely that these modular bases will actually be an orthonormal basis of the space of continuous functions on ZP. So let's start with each of the steps here. So step 2. How do I do step 2? Well, I'm just going to give a rough idea of this. So this is rough. So basically, I will show, because I take this thing here, I take the m difference of this. I want to show that as m goes to 0, or excuse me, maybe I should say, so say when k is sufficiently large, then the Banach norm of f taking difference p to the k times. No, excuse me. This is less than or equal to, maybe I should say, let me just write p inverse times the original Banach norm. And therefore, you see that if you take, so then this would imply that if I take f n, if I apply this sort of repeatedly for n really large, this will be very small. And thus, in particular, if I take either the value at 0, or maybe I just write m. If I take that value as m, will be very small. So that proves the first step I want to prove. So all I need to prove is that when k is sufficiently large, if I take enough times difference, I will reduce the Banach norm of the function by at least 1 over p. And of course, I particularly want is the number of times I take difference to be a power p. That makes our calculation a little bit easier. Okay, so which is bad here. Let's cut this and move it all the way. Yeah. You know what? Let me cut it. Sorry, I have a little bit of trouble to organize my page. Put it somewhere. Sounds good. Okay, so let's prove this. So here's the idea. The idea is a little bit brutal, actually. So you want to really write down what it is from the definition. The definition is here. If you do it once, you take the once difference, and then you take n's, you take the different, so repeatedly n times. Now, if you do p to the k difference, then what this end up getting is, if you write it down, it looks like the following. So the main term are these.
Liang,
next, there are lots of.
Liang,
Alvaro.
No, when you wrote
saying something.
You wrote the mth difference of f. You don't have any relation. Do you mean less than or equal to something?
Sorry, I didn't hear you. Pardon me.
You wrote the mth difference of f.
Mm.
What about it? Is it supposed to be less than or equal to something?
Oh, yeah, okay. This is this goes to 0 maybe, or like, very. I said very small. Okay. I don't know. Very small. Yeah. Sorry. Okay. So let me finish this. I mean, so these are the terms that I really care about, and of course, it's not just that. You have a sort of a binomial coefficient term, and then fx plus p to the k minus I, basically. You have these terms. I mean, basically, you can kind of check that. If you do 2 of these, you will get fx plus 2 minus 2 fx plus 1 plus fx. So the 2 is already kind of a binomial coefficient 2, 1. And if you keep doing that sort of p to the k times, that's the expression you have. The reason I wrote it in this way is because I want to remark that this term is already divisible by p. So in terms of norm, this is already, has a kind of a 1 over p here. So this entire term, we're good. Now I have to deal with this part. This part, I want to say that this part I use the following fact that because ZP is compact and have a continuous function f on this one, so therefore this will imply that f is continuous. Maybe I should say comma. F is continuous, and these two will tell you f is uniformly continuous. And therefore, if you know that plus p to the k means that x, but we know that this is very close to, because I'm adding a huge power of p. In the p-adic norm, a huge power of p means very, very small. So these 2 points are very close to each other, and the function is also uniformly close. So therefore, when k is large enough, this thing has, this thing basically will go to 0. The difference will go to 0. And therefore, you see that as this k gets really large, the total norm, and also this is sort of uniformly for every x, and this total norm will be less than equal. This total norm will be less than equal to 1 over p of the actual norm of p. So that allows us to show that after you take differences operators enough time, the norm will actually decrease, and therefore the value at 0 will actually go to 0 as m large enough, and therefore these coefficients, the Mahler basis, the sort of Mahler coefficient we had earlier will go to 0 p-adically. So that proved step 2. That's probably the one of the most difficult part. Well, this takes a bit of time. It takes a bit of some work, I guess. I don't know. So step 3, I want to show that whether fx is equal to the Mahler expansion a n xn. Okay, so let's maybe take the difference. And maybe I should also say that because this an has p-adic norms go to 0, now this sum will converge absolutely. Will converge to something, or converge to a nice function. Okay, let's take the difference here. What do we know about this difference? First, I know that if I evaluate at 0, I mean, we show that that's how we get a 0. So this is 0, right? We also evaluate 1. We know that how we get a 1. We want these two be equal at 1. So this is again 0. So basically, if I evaluate any positive integer, this is 0. But on the other hand, this whole thing is continuous. Because the an converges nicely to 0, and this will converge to a continuous function. The difference will also be continuous. But it's a continuous function that takes 0 at all the positive integers. And we all know that this n is dense in ZP. We've been using this many times. So these two altogether says that the difference is 0. There we go. And that's precisely what we want for all x in ZP. So now we really show that there's a Mahler expansion, well-defined Mahler expansion. That's kind of nice. So lastly, I want to show that this is how should I say it? This is actually form also normal basis, the smaller basis. Let's do that. Step 4. I want to show that norm of xm is 1. So how do I do that? Well, first of all, for any x in ZP, we show that this really takes value in ZP. And therefore, this definitely will tell me that the norm is definitely less than or equal to 1. because it takes p-adic integer values. So therefore, the p-adic norm of p-adic integers are always less than or equal to 1. That's great. But on the other hand, I can take x equals to m. Then x equals m, choose m, will equal to 1. And so means I do take, and I do take some value whose p-adic norm is 1. So combining these two together, I see that the norm of x choose m is precisely 1. That's one thing. So now let's do something a little bit more complicated. So what about if I have my f written as in terms of the Mahler expansion, like that? Now I know that if I take the Banach norm of f, that's going to be less than or equal to, well, because of the stronger triangle inequality, this will be the max of all the norms of an of xn. But this is the same as if you scale something, that's just you can take the norm of scale out. And we've seen this is 1. So this is nothing but just a max of an p. So it's less, so f, the norm of f is less than or equal to this, for sure. Okay? So the question is whether this could be smaller or not. Right? Could it be, so all I have to show is that whether this could be strictly smaller or not. Now I go back to how I get this an. So let's recall that my each an is something like fn plus some number plus minus some number minus 1 plus minus some number fn minus 2, and so on and so forth, plus minus some number in f0, right? It's going to be some sort of linear integer coefficient, linear combination of the values of f. And therefore, this will immediately tell you that the norm of AP is really less than equal to maximum of this f of I for I between, I guess, 0 and n. And this is certainly less than equal to the norm of f. So now, once you have this, the right-hand side is definitely less than equal to the norm of f. Because, each one of them is less than equal to the norm of f, therefore the maximum one must be less than equal to f. So we're done. We have, all of these two must be equal. And that really shows our theorem that these binomial functions, or the Mahler basis, they form an orthonormal basis of this space of continuous functions on ZP.
Liang?
I'll stop here. Yes.
Yeah, there's actually a question, which is the most common question in a number theory talk. What happens if p equals 2? Does this break?
This one doesn't break. No problem. Yeah. So this works for p equals 2. Luckily. I agree. Lots of things fails for p equals 2, but this one's okay.
The follow-up to the question is, let me read. So I think the concern is about when you have f of x plus p to the k minus f of x, it relies on p to the k being odd, so we get minus and not plus. Yeah, that expression.
Good point. I guess I could possibly avoid this by
it doesn't rely on p
by using 2pk if I want to, and this would automatically be f of x plus 2pk minus 2 times this plus fx.
It does not rely on p being odd. Minus signs just come from the difference calculus. It's not an issue of even or odd. It all goes through. That proof is.
No, it does. Like f2 is just, you see it here.
Yeah, but the plus or minus signs are coming like you have a minus sign in the second difference. automatically, not an issue of even or odd.
No, I think it is here.
The Mahler coefficients have alternating minus signs.
I have to think about it. Maybe I'll think about it and get back to you. But
Okay.
I do.
Yeah, thank you.
I mean, here's a resolution, right? I mean, like if p equals, I mean, I can do 2p. Oh, bad. I can do some sort of 2pk, and that's going to be what am I doing? So then I have this minus 2 times that plus this. If I have uniform continuous, these are essentially sort of the same number, and then I can cancel things this way. Just have to do some multiplication. Very good question. Well, that's sharp. I didn't realize that.
There's another question, Liang.
Yes.
Could you remind us why the elements of the Mahler bases are orthogonal to each other?
So that's a very good. So the question, or rather, question: what does orthogonal mean? Right. So it's different from when you have inner product structure. You take your inner product, whatever. Orthogonal is maybe I should. I mean, but after a while, we don't take quotation marks anymore. Orthogonal just mean this. By definition, orthogonal means this. So what that means is that, for example, xn is orthogonal to the other one is saying that this function, the norm is basically, I mean, or rather, if you take any sort of linear combinations of a xm plus b xm, this is exactly the maximum of p-adic norm of a comma p-adic norm of b. That's what orthogonal means. So it's not quite sort of there's no inner products. You can't say that. Just that. I guess the slight difference is that in general you always have inequality this way, but orthogonal means that you always have equality. That's precisely what we proved here. Yes. Other questions? Comments?
No. We've cleared the deck. Thank you.
Yes, good. So now I'm going to turn to the dual of this. Takes a little bit of sort of mind twisting, but okay. So let's do dual. It's called p-adic measure. It's like you have the space of functions, continuous functions on ZP, and I want to take the functional on this. In a sense, a measure on ZP with values in QP, it's just a continuous linear map on the space of continuous functions. So basically for any function, you specify a value in QP, and that counts as a way of telling you how to integrate. This is maybe if you first see it, it's a little bit weird. I mean, like over R, there seems to be a unique way to how to do integration. This is Riemann integral or Lebesgue integral or whatever. But for p-adic, well, there's no that usual integration thing completely fails. I guess because of the following. For example, if you say, okay, if you say, okay, say volume of ZP is 1, say you want to do that. Okay, that's fine. But then what about volumes of 1 over PZP? Excuse me, PZP. You see that, I mean, if you have a reasonable volume, the constant volume with p-adic numbers as sort of values, so these I plus PZP, or maybe I just write PZ. Just 1 second. This must be the same as volume of 1 plus PZP. And it doesn't matter which residual disk you take, must have the same volume. And the total volume must be ZP as well. So if you equal these two, the volume is 1 over P. But this is okay in the over R. 1 over P is small. But in the p-adic world, 1 over P is huge compared to 1. So that's kind of a very counterintuitive, right? I mean, if you pass to a smaller subset, turns out volume is something large. I mean, okay, but then the problem is there's no way that if you take sort of, when you do this integration, in the sort of naive way, there's no way this is going to converge, because what do you mean by integration? If you think of it in terms of Riemann integration, this will be some sort of limit, right, of sort of sum of all the residue things, right? And then put a sort of volume of volume of I plus p to the n zp with some integration, with some sort of values maybe, right? That's what you would think, that's what you want to do. But then this thing is 1 over p to the n. I really can't think of a way to make this limit work, right? Come on. You have 1 over p to the n here. This is a huge number in p-adic world. So instead of really defining a Riemann integral like that, the solution is just forget about sort of breaking apart this thing. Just say a way to integrate functions is just a continuous linear map on space of continuous functions. But there are going to be many ways to do that. This is called a measure on ZP with values in QP. So d ZP, comma, QP will be the set of all measures on ZP with values in QP. So here's a theorem that gives you a description of all the measures on ZP. It's better to, it turns out to be, I'll show you explicitly what it is, but why to say it this way. But all measures on ZP can be given just explicit as a power series, like that, where B1 plus B0 plus B1T and going onwards. And these BIs are QP, p-adic numbers, and they're uniformly bounded. So namely, there's a sort of a common denominator happening here. So explicitly, so if I have a measure here, I have to explain what it does. So what's the value of this on a function? So for fx, written in terms of modular basis, continuous functions on ZP. Then I define this measure, namely, so this is maybe I should say this integration is just kind of think of it as kind of a symbol. It doesn't have any meaning of the Riemann integration or anything like that. It's just a symbol, or rather, you should think of it as a pairing between functions and measures. But I still want to write it like that. Looks like we're taking the integration, but I'm just defining it to be, well, maybe I should do it this way. So what I want to ensure is that if I integrate the standard function, namely a modular basis d mu x, I want it to be the nth coefficient of the power series I wrote down earlier. And if I integrate fx, so it has to be a linear combination of these modular bases, and therefore you see what's going to get. You're going to get a0, because this is equal to what a0 plus a1 times the first element in the modular basis, and so on and so forth. So this is just a0 b0 a1 b1 plus a2 b2 and plus all the way. It's an infinite sum. But what makes it somehow we know that the pi norm of an goes to 0, and the pi norm of bn is bounded. And so therefore, if you multiply them together, the pi norm goes to 0, and therefore this thing converges. So that explains why I need this bi to be in QP and uniformly bounded, because I can apply it to each one of them. Okay, so basically, I guess the space of all measures on ZP is kind of a dumb, essentially. It does. I mean, at this moment, I didn't explain why I want to write it as a power series. It could be just sort of a sequence of numbers, B0, B1, B2, and so on and so forth. Basically, you evaluate on each nth element of the modular basis, you just get value Bn, and you sum them up like that. But it turns out that somehow writing in the power series has a very cool way, sort of have a very cool explanation. So this is something called maybe Army's transform, or Army's transform, probably. Probably his French. She? Is it she?
That Amis.
Sorry, my bad. I should have known. So basically, given the measure mu, the associated power series A mu t can be given. So basically, as I said, somehow you just have this. Suppose you just this measure just these sequences. But the reason I want to put them in the power series is because precisely the following expression. So I can write it as a completely formal expression. 1 plus t to the power x. I'm integrating x. You can say this is a completely bizarre thing. But let's sort of, I think of it as maybe think of it as kind of just formal expression for now. But let's unwind this formal expression. So remember that we talked about this binomial coefficients thing, right? If I have some actual integer n, then the binomial expansion will look like the following, like that. So supposedly this formal expression, I should understand it as integration on zp with summation of n greater than or equal to 0 of xo. Maybe I should write I, because I use I here. Oh, sorry. X choose I times t to the i's power of d mu. Okay. And if you believe that in the p-adic everything works extremely nice, so I can swap the integration and sum. Maybe I can also take out the t to the I, because this is a formal variable, doesn't have any meaning for the integration. Now what you see is, I remember that my mu defined in such a way, if you integrate a binomial function on that, you just get bi. So you see that that's why, in some sense, why we write this power series expression. It's because I have this sort of beautiful formula. Amis transform like that. This is, I think personally, I think this is a very cool formula. Maybe I should let me remark here. There's another reason why. There's another reason why people write these measures this way. That's because there's something we should notice, that the power series has a multiplication, right? So you can ask, what does sort of a multiplication mean? Right? You have two measures, mu1 and mu2. They have some sort of associated power series. And power series, I can multiply them together. It does have a meaning. It's precisely the power series associated to so-called the convolution product of mu1 and mu2. In the following sense, that if you integrate a function for the convoluted measure, okay, by definition, what that is you're integrating zp cross zp of f y plus z of mu1 y, mu2 z. In the sense that I call it convolutions because it looks really like convolution, of course. Also, you should, if you're somehow, it's really convolution with respect to additive group for zp. And in some sense, you should really think of this. I mean, this kind of you have seen it somewhere. If you, this looks like Fourier transform in some sense, or like maybe Laplace transform. In the sense that, if you take some sort of convolution product under Laplace transform, it corresponds to the multiplication. It looks somewhat like that. But sort of p-adic can't quite. Yeah. Anyways, maybe I'll stop here and wait to see if there's any questions about these. Okay, sounds good. I'm not sure how I'm gonna proceed. my goal of this whole lecture is that I'll eventually talk about a p-adic version of Riemann zeta function, which will be written in terms of a measure on not quite ZP, but ZP cross. But that's why somehow I took this all trouble to go through the space of bonus, space of functions on ZP, and then talk about the measures. But on the other hand, this is cool. I think these are all very cool things that you don't usually see elsewhere. Anyway, let's try to go somewhere, and let's sort of get prepared for maybe the next 10 minutes to get prepared to talk about this p-adic version of Riemann zeta function. It's called Kubato-Leopold p-adic function. Let's go. Maybe I'll go through the analytic part now. So let's see. So here's a slogan. What is a sort of p-adic function? What does it do? So in some sense, I want my p-adic function to p-adically interpolate special values of negative values of the Riemann zeta function, which turn out to be rational numbers. We know that the negative number at the zeta value at negative even numbers are all 0, so there's nothing to talk about. But the odd numbers, so these p-adic function so this L function will be kind of a p-adic function in some sense, or p-adic measures. This will encode the value of these. One of the ways to explain what's happening here is that, why we do this is that this gives a systematic way to explain a congruence that's discovered by Kummer, which is proved by I don't know. This is 18. So that's 19th centuries, right? So Kummer proved the following: if you have a odd prime for any k greater than or equal to 1, if I have two numbers, n1 and n2, they're congruent modulo p minus 1 times a high power of p. And suppose that these n1 and n2, they're not congruent to -1 modulo p minus 1. This is a technical condition, that ni plus 1 is not divisible by p minus 1. And this n1 and n2 are not too small. They're bigger than greater than or equal to n. Okay. Then we have this sort of strange congruence, really. This special value of zeta functions as these negative numbers when n1 and n2 are really very two different numbers. They're very far apart as integers, but they are somehow very close as p-adic integers because their differences are divisible by a high power of p. And also, of course, at the same time, they must be also kind of congruence modulo p minus 1. They must be, and the value of zeta function at these 2 points must also be congruent modulo high power of p. So in our language, this number will be p-adically very close. So maybe I write it this way. So basically it says that if n1 and n2 are p-adically close, that implies that zeta of negative n1 and zeta of negative n2 are also p-adically close. So this was proved in the 19th centuries, but somehow people really didn't quite understand. Of course, people understand logic, of course, but doesn't really have a more philosophical reason of why this is true, except we have a proof, or rather somehow something that tells you that before seeing the proof tells me that this has to be correct anyways, whether you could give a proof or not. And probably in the 1960s, or maybe a little bit earlier than that, during the development of p-adic theory.
Liang, I think I lost you. I can't hear you.
You can't hear.
I can.
Oh no, I can hear you now. I can hear you now.
Okay, strange.
Yeah.
Where did you
we're
lose me? So did you see I wrote this? You saw I explained this?
Yes.
I think that's the first thing we didn't hear.
Oh, I see. So you heard me explaining the congruences, the theorem.
I think so, yeah.
Okay, sounds good. I'm just repeating what theorem says. It basically says that if n1 and n2 are p-adically close, then the zeta value of negative n1, negative n2 are also p-adically closed. That's basically what Kummer congruence says. So it's a very sort of a very interesting way of like it has to be some reason behind this basically. But when Kummer first proved it, of course he has a correct proof, but people don't really understand why. I mean, in my understanding, a proof would be sort of the correct proof if basically somehow tells you that without going through the logic, it tells you why this has to be the correct thing. Right. Anyway, but this is not known until maybe probably 1960s, when p-adic theories are largely developed, and also has influence of EOSR theory. So people started to think about this so-called p-adic functions. So that truly explained why this is true. So maybe here's given some example of this Kummer's congruence. For example, p equals 7, I take k the congruence to be 2. Oh, sorry, k to be 2, and therefore p to the k will be this p. So now p minus 1, p times p to the k minus 1 is just 42 in this case, 6 times 7. And I take two numbers, 3 and 45. If I take zeta value of negative 3, it's 1 over 20. And if you expand it, it's like 1 plus 4 times 7. If you take zeta value at negative 45, so Sage can probably tell you this. And if you do it, really expand it, the first two terms is 1 plus 4, 7. You see that these are somehow the same. Let's do a non-example in the sense that I do need this ni plus 1 to be not divisible by p minus 1. So here's again this p equals 7, k equals 2, I take 5. But note that 6 will divide 5 plus 1, and therefore this condition will fail. And what happens is that somehow take these zeta values, there's a 7 in the denominator. So they can't be congruent to modulo high power p in some sense. So I think this denominator can also be explained somehow by what I'm about to explain. But I guess I'm not so sure I want to talk about the proof now. Maybe I'll record something and post this on the webpage to talk about the proof of Kummer's congruence using the things I've talked about using p-adic measures. So maybe for the last 5 minutes, let me sort of jump to the end. Oh, whoops! I didn't really have that, did I? Or maybe I have it here. So let me sort of get to the end of somehow the story to tell you in real time what somehow what we're expecting. So the idea is that somehow the pi zeta function, this is called Kubota-Leopold p-adic function, is actually a measure. So it's a measure on. It's not quite. It's basically at this time it started out as the correct way to formulate it is it started as a measure on ZP, and you restrict it to ZP cross. So maybe I should say that D of ZP cross of QP. So your Kubota-Leopold p-adic function kind of belongs to here. And there's an additional A. I'm not going to talk about the technicality here, but that's a correct way to define a p-adic function. And what it satisfies, the condition what it satisfies is that for every n greater than or equal to 2, if you integrate the function x to the n, this sort of power function, or rather you should think of it as a kind of a character function, in the sense that you're taking the character of sending x to the n. It's a multiplicative character. If you integrate this thing on ZP cross, what it will get is that, or I should say, what A is just basically some number in ZP cross, such that this is not this is also in ZP cross basically. And I mean, if n plus 1 is not divisible by p minus 1, such that when you let me get to the point. So such that when you integrate this character here, it will essentially give the zeta value at negative n. And somehow the congruence between zeta negative n is turned into the congruence of these characters x to the n. For different n. It's really comes from the congruences of the character x to the n. Because we know that x to the n is very much congruent to x to the n plus p minus 1 times a p to the capital N, a huge. So these are very much congruent modulo, probably p to the, I can't think right now, maybe n plus 1. These are congruent. And therefore, the corresponding zeta value will be also congruent to that number. So that's the upshot. In the sense that in the p-adic world, in some sense, the p-adic function is not quite the correct way to formulate the p-adic function is not quite a function, but rather a p-adic measure. In an even more fancy way to explain what this ZP cross is, this is somehow related to what Keith talked about, is that the ZP cross is really, the Galois group of the cyclotomic field of QP. And this character, the nth power character, should be really thought of as a cyclotomic character to the nth power. So somehow, if you take the measure and you couple with this cyclotomic character to the nth power, you should get the zeta value at negative n. So that's basically sort of the philosophy of sort of p-adic function. 1 minute, let me just sort of go crazy and talk about what's sort of in general. So so in general, you have lots of sort of way to say L functions. If you have heard, well, probably we didn't really do that. If for those who have known L functions, for those who know sort of module forms, there are L functions attached to module forms, and so on and so forth. For each sort of the usual L function or zeta function or generalization of a zeta function, conjecturally there should be a way to make that into a p-adic L function. But every time the p-adic L function will be some kind of a measure or in general distribution on ZP cross. And it should satisfy some conditions, properties like the following. If you integrate some x to the n power, and this should be up to some simple factors, being your L function evaluated as some sort of particular integer place, where this n corresponds to the n here. So that's sort of the general philosophy of p-adic functions. And I guess I'll probably end here. There's a lot to explore after what I talk about. So what I talk about is just sort of very basic things about p-adic functions on ZP, and I hope that this will lead up to something sort of more interesting and more advanced study. That I hope you will be interested in going forward to explore these in your, I guess, career, like in your PhD study in the future. I guess I'll end it here, and hopefully I'll add another video to explain the construction of this measure, which is very explicit, turned out. Yeah, I'll stop here.